Hi guys, so I just have a quick request. All of you who have posters up on the boards, please during the breaks, would you please go take them down? We need to have the boards returned today and they're coming to take the boards down around about lunchtime. So if your poster is still up there, not a big problem, we're going to take it down and put it someplace safe. But in the meantime, if you would just go take them down, we'd appreciate this. Thank you.
Welcome everyone to today's first session of presentations, and we have 6 interesting talks lined up, starting with Athanasios Yavas-Ramaya talking about AIM-FAST, an astronomical image fidelity assessment tool.
Hello everyone, my name is Athanasios. So today I'll be presenting an in-house developed tool called AIM-FAST. This is an image and catalog assessment tool. Without any waste of time, let's get into it. Some background introduction is that AIM-FAST is a pure Python package, and it's hosted on GitHub and published on PyPy. It's meant to be an intuitively visualizing astronomical catalog tool, and it can also be used to cross-match catalogs, and this include online catalogs such as NVSS. And the nice thing about it is that it can also be easily integrated into workflow environments or used with source finding software. And then also you can use it for image statistics. So just some basics is that, for instance, we know mostly in astronomy, we're interested in making images and catalogs. So in your catalogs, mainly you have your source properties. And in the source properties, this include properties such as flux, positions of the source. So what you can do with AIM-FAST is you can directly plot these properties. For instance, here I'm showing the array index, so directly you can just visualize the array index of your catalogs, and also you can plot any column. So at the moment, there is a handful number of catalogs that we support, but feel free to suggest any catalogs that you like us to include. So these basic visualizations can help just to get an overview of what your catalogs include. For instance, if you see on the right plot here, we plot the flux against the spectral index, and also if your catalog has uncertainties or errors of those properties, you can also plot that. So for instance, what a user can get out of this, you can see, for instance, information such as if your flux reduce your uncertainties. So these are the kind of stuff that you can tell. Your flux, when your flux decreases, you can see the uncertainties and the SPIs increase. So already you can tell also at what value are those uncertainties. And the nice thing is that it's based on a tool called Bokeh. So Bokeh is a visualization tool. This allows you to do the basic zooming and hovering your mouse to get some information about that specific source. Say you're interested in a specific source that which you want to extract some information about. For instance, if you hover your mouse. So here it includes this table as well, so you can select the specific source in the table to get information or to highlight only that specific source and also get its specific information. For instance, here we selected source 8, or also you can just hover your mouse to get specific information about that source. And then going to the cross-matching. So in the cross-matching, so currently we cross-match photometry and positions. So with the photometry, as you can see, also with the same interactivity, you can view source information and all that. And also, so when you cross-match, since we expect a linear kind of relationship between two catalogs, if we are cross-matching them, we do a linear fit to get some statistics about that, and also we give a table of sources that did not cross-match from both catalogs. So you can just have an idea how many sources are not cross-matched, and also maybe you can do further investigations about those sources. Also on the statistics, sometimes you can get outliers. What you can do also when you cross-match, you can exclude certain sources. So if you know a source by its specific source ID, you can exclude it from your cross-matching, maybe for other particular reasons. So you can get your basic statistics. And then same as the astrometric measurements. So you get a position offset of the two catalogs. So for instance here, I show, so here we show the position offset in array and DAG. And also if you look closely, there's a blue circle. It's not showing really nice because of the error bars, but basically it's the sigma of this distribution, and then also there's a table, I didn't include it here, so that table can tell you how many sources fall within this one sigma, and how many sources fall outside that, and also you can kind of get the completeness of the cross match. And then on the right hand side, what we show is just an overlay of two catalogs, just to get an idea. And also you can still hover your mouse to get specific information about particular sources. And then going to the statistics, so you can get basic image statistics. So for instance, one other statistical visualization is that, so mostly in astronomy, when you make images, in radio astronomy, they perform this process called deconvolution. At the end of that, you have a residual image. So in the residual image, it tells you the basic residuals. It shows you the residuals of your data after you do deconvolution. So you want to have an idea of how sources were well deconvolved. And on the left plot, we show random residuals. So we just generate random positions in the image, and then we calculate the sigmas within a specific region. A user can specify a certain region that they want to calculate the specific statistics, and then you can, as you can see here, you also can get the ratios of that. And then on the right-hand side, which it's somewhat important so this one uses, after you make a catalog, it uses that catalog to go to the positions of those specific sources and calculate the residuals. So this can give you an idea if there is some source residuals left at those specific source locations. And then further on, you can get sub-image statistics. So if you're interested in a certain region in your image, you can go there and get the statistics that are listed in the table. Also, you can compare. So if you have two images, say you ran a certain process and you ran another process on the image, and then you just want to get an idea of how the processes went well in comparison to one another. So, for example, in the top row, it shows, for instance, in this case, it was an image after performing direction-independent calibration, and then on the right, this direction-dependent. And you can see the statistics, and you can compare for that particular region that you're interested in. And actually, to mention the main reason we developed this tool, so it was part of my MSc project working with Oleg and SPE. So we wanted to investigate different imaging softwares. So just kind of get an idea, because we know that there's an outburst in softwares in astronomy, and even softwares that perform the same particular task. So we kind of want to gauge which one kind of performs better, or which one performs better at a certain observation as an observation result. So for instance, a user might be thinking to choose one software. So we build a pipeline, and as you can see in the pipeline is that you have all these different tools, and then you can perform your analysis at the end. Basically just showing the plots that I showed earlier on. You just plot all the statistics, you compare the catalogs, and then just see. And this framework was built using STIMELA, which was presented yesterday. And these are some of the results, same particular plots, and then you can compare those. And then similar to residuals, you can see which residuals. And then another useful use for this software is that you can use it within a pipeline to, say, run particular steps in an iterative manner, using the same plot and statistics to gauge if your processes are going the right manner. For instance, here you can run like different rounds of imaging and then compare the residuals. And from there you can tell if you are improving or not. And the nice thing is that it's a command line tool, and you can just run it on the command line or in a workflow environment. I think that's the end of it.
Thank you very much for that interesting presentation. There was a question on Discord from Oleg. Do you want to ask in person?
No, just a technical question, or maybe I just missed it. But when you say it's run from the command line, what are the output formats for the plots and for everything?
So the output formats is HTML files. So Bokeh allows you to save these HTML files. So you can open them in any web browser, and it allows you for that interactivity. So HTML files are the products of InFAST.
And I see there is some typing going on, yes. SPE has sent a question on Discord, and he is asking, what did you find in your image comparison experiments?
So in the imaging comparison experiment, for example, here I'm showing photometric results from CASA and WSClean. So the differences are not much, from what we found. For instance, as you can see, so one of the things that you can use to gauge that is that, so the slope, you expect it to be 1. As you can see in CASA, it was like about 86, or 0.86, and in WSClean it was 0.93. And this was tested on extended sources, so this way we generated random Gaussians. So I would say the results were not much of a difference, but from the statistics you can kind of gauge which one is close enough to the slope that is expected.
And we do have one more question and time for it. And the question is from Dirk, who asks, concerning image fidelity, can you give it two FITS files of different resolution and check how they will agree?
Can you repeat the question?
I can repeat that, yes, sorry. So concerning image fidelity,
Yeah.
can you give it two FITS files of different resolution and compare how well they agree?
How well they were cleaned. So
No, how they agree.
how well?
They agree with each other.
How well they were cleaned.
No, how well they agree. Well,
Oh, yeah. So one thing that I didn't mention is that also we try to incorporate different source findings tools. So at the moment we have WSClean, PyBDSF and AGN. So if you have two images per se, let's say, and these are restored images with sources in them, you can run a source finding software on the fly and then generate two catalogs and immediately compare those catalogs.
thank you very much. And if any further questions, please do use Discord for asking them. Let's
Okay.
thank the speaker again. Before moving on to the second presentation, I forgot something actually, which is to introduce myself. My name is Christian Hettlage, and I'm working as a software engineer at the South African Astronomical Observatory. But more importantly, our second speaker is Marco Molinaro, and he will present about supporting fair principles in the astrophysics community, the European experience.
Okay. Hi, I hope everybody can hear me. My name is Marco Molinaro. I'm part of the Italian National Institute for Astrophysics. This contribution is being prepared by me and the other colleagues you see listed here on the right side of the slide, and provides with a, let's say, the European perspective from the ESCAPE project in supporting fair principles in the astrophysics community. I won't go through the FAIR guiding principles. They've already been detailed a lot in Simon O'Toole's presentation on Monday. And some other info came from Mathieu Servilla's presentation yesterday related to the CTA experiment. And there are also other posters and contributions that deal with them. So here I will only give you an overview of what the ESCAPE European project is doing with this FAIR principle. And this is done in connection to the, let's say, the IVOA architecture side of it. So as Simon reported, when you start out of the VO technologies and standards, you are already in good shape for being fair with your data and services. Maybe not completely. I just sketched here on the right-hand side a small overlap of the architecture that Simon has shown and how I see it representing the FAIR principles, where reusability actually encompasses all of the technologies and standards and need all of them. Provenance is possibly one of the big deals there in doing reusability, while interoperability is at the core of the system. Being part of the IVOA, the EuroVO is simply the way to connect and coordinate European activities in there in the VO landscape. On the left side, you see that historically this has been, let's say, side to side with the IVOA for a long time. And nowadays, the VO activities are mainly dealt with within the ESCAPE project and in a work package explicitly that is called CIVO, that stands for Connecting Espree Project to EOSC through the VO framework. So this is sort of an acronym soup and a short introduction to the ESCAPE project that you can check also. There are other posters for this also. So ESCAPE is the European Science Cluster of Astronomy and Particle Physics ESFRI research infrastructure, where ESFRI is the European Strategy Forum for Research Infrastructure. So ESCAPE tries to put together the ESFRI important infrastructure or critical, crucial infrastructure and try to lead them together into the European Open Science Cloud solution. The CIVO Work Package 4, tries to use the virtual observatory technologies and architecture to have ESFRIs connect in the EOSC side. And this is mostly what I will be dealing with in this presentation. This is a quick overview of the points that I will be touching through. So, well, I won't read them through, but it's mainly some technical work that has been done. How do we support standards for interoperability in the IVOA? And also a couple of more points about software interoperability and fairness in terms of the cluster of projects that we are dealing with and the metrics that are related to fairness. One first activity that has been carried on in ESCAPE and is continuing is the integration of the IVOA registry in the European Open Science Cloud landscape. So currently what's been done is that the UDAT B2Find repository that is part of EOSC carries the VO registry content. How it does so? Using the Open Archive Initiative Protocol for Metadata Handling Harvesting solution, data-side metadata are harvested from the VO registry into the B2Find solution. And the ongoing work is to specialize it into the B2Find metadata that sits on top of data-side, but is, let's say, customized and made more concrete for the B2Find solution, like, for example, adding instruments into the metadata. The VO resource, that is the metadata schema for the IVOA registry, to the data side mapping is not complete. The most important thing that is missing is the per protocol access URLs that the VO registry carries, and this cannot be completely mapped into data side. Also, there is not really a support for table set solution, only general resources. On the other side, the Unified Astronomy Thesaurus, the top level concepts of it, has been mapped into the VO resource and are available also through B2Find. On top of that, as a small effort, but is something that we will try to keep on, is trying to go cross-disciplinary. So bridging the boundary of astrophysics or particle physics with other disciplines, maybe Earth observations. To do so, some user stories has been sketched. You can see there a link to the place where they've been reported. And it seems anyway that there is more a problem in discovering the collaborators in doing cross-disciplinary science rather than discovering the resources there. Similar, or let's say alongside the integration, there is also the idea of onboarding directly VO resources into the EOSC portal. To do so, we have set up a provider within EOSC. We use the Italian National Institute for Astrophysics as a test provider for that. And we picked up a couple of resources, not actually VO registered resources, in collaboration with the NEANIAS project, to try the onboarding procedure that is done through web form, authentication of the responsible person for providing resources and such. What we will do in the near future is to start from VO resources directly so we can report to the community some guidelines not to duplicate efforts in registering resources both in the VO landscape and on the EOSC platform. This is because there are differences between the IVOA architecture and the EOSC one. I've just bullet listed some on the right-hand side here. Not only tasks of integration have been carried on, what continues to be done is supporting the IVOA standards and upgrades on the European landscape. IVOA interoperability meetings, one will follow just did as now, are kept as milestones to report the results that have been obtained there. Specific results that we'd like to mention are the radio astronomy data access that is ongoing and is discussed, or the interoperability standards and tools to support multi-messenger in follow-up of gravitational wave events. On the table here on the right-hand side, there are more specific developments and standards updates that have been done within the ESCAPE project with this respect. To disseminate, to have a complete, let's say, community, you need to have an open, aware community. So the community that is aware of the tools and technologies that are there to let interoperability and fairness be ready. And this is the way the VO schools are a way to do so. I won't go into detail because yesterday Fran Jimenez has given a great talk about this, and I don't want to stall anybody, something that is already been done. And switching to another thing, usually in fairness, you think about data resources, but there's also the need to ease the publication and integration process for softwares. So there is another package in ESCAPE, that is WORK Package 3, that is the Open Science Software and Services Repository, OSSR, that is doing a work that is sketched here on this diagram. So you have a GitLab solution to develop and maintain software that you can tag. And after that, you can publish your source code or Jupyter notebooks, maybe directly on Zenodo, build container images that can be published again in Zenodo or on Docker Hub. And to have a longer term and integration into EOS ESCAPE, you have the final link through this repository into the ESCAPE one. Directly connecting to this and the software interoperability, there is an activity going on. It's, well, more or less just started, that deals with how to do with lots of different tasks that are currently in use in the community. So these have different interfaces, behavior, they are differently configured, you have different authentication schemas to deal with. So how can you make these interoperate? You cannot possibly think of merging all of the features that they have, but you can try to select specific functionalities to constrain the interfaces and identify a minimal set of functionalities there to reach interoperability. To do so, there is the need to try to implement these different solutions, so Jupyter notebooks, Docker containers, and whatever else you can think about. And then once you have that in place, try to answer the, can I run this task type and mode that you have to add there? In a sense, how can I, authenticated person, run a task on top of some resources in a mode that can be maybe synchronous or asynchronous or such? I suggest you to check the Can I Do This talk that Dave Morris gave at last May Interop for further details on this part. Finally, interoperability cannot live within a single system. Being it a cluster, a domain, a project, or being geographically bounded, interoperability have to bridge and go over those boundaries. So ESCAPE connects to EOSC also through other projects. For example, the FAIR project, where Mark Allen has been considered an interoperability, a champion for fairness for astrophysics, and participated in activities in turning FAIR into reality. With the Freya project, we participated in the discussion on persistent identifiers, bringing in the IVOA IDs experience. There has been also testing and discussion at RDA level for the FAIR data maturity model, discussing the model, the proposed metrics, and also the goal of the metrics, because FAIRs are guiding principles, and you have to be careful not to consider the metrics out of those guiding principles to be something that judges your resources. They should be really guidelines for you to go further into the fairness of things. And also the solution for stewardship, curation, publication related to S3 archives has been presented at LISA 9th conferences. At European level also we have connections with the Europlanet community and the VESPA for solar and planetary physics access, the SolarNet people, and the NEANIAS project that deals mostly with the technical infrastructure of cloud. So as I said, all what I've said will continue on in the next steps of the project. Some details you can find better detail in 2 ESCAPE deliverables that are linked here and will be in the presentation slides when you check them later. In summary, ESCAPE CIVO continues to keep alive the interoperable astrophysics community in Europe, so under the EuroVO, connecting to EOSC, giving continuity to international collaboration and working on new challenges while upgrading existing ones, a challenge like connecting to the EOSC itself, for example. And FAIR principles and open science are naturally embedded in the VO architecture. And this is also proven true while trying to connect it to the EOSC landscape. One thing that is important is that FAIR principles are made also aware of the automation that you can do in fairness, but it's important to consider that interoperability will also require human intervention. This has been clearly stated and reported in a recent talk last week by Claudia Mertens in the first FAIR webinar when dealing with metadata exchange issues. And finally, interoperability requires open standards, and these need to be driven by community. Thank you for your attention.
Thank you very much for that presentation. I see no questions on Discord. Are there any questions from the floor? I see none either, then I have a quick one. You mentioned as one problem that discovering collaborators is difficult. Are you trying to address that in any way?
Well, I'm not direct, well, I'm involved in that, but Markus Diemleitner is the one that is really pursuing that task activity. And especially with the Earth observing community, Earth observation community is trying to see what use cases and what collaborators could be found to define use cases that really attach to the discovering and access data that come both from astrophysics, so looking up, and Earth observation that is looking down. It seems to be more difficult than expected to do so.
Thank you very much indeed, and let us thank the speaker again.
Thank you.
Our third presentation is from Nuria Alvarez Crespo, who will talk about ESA Sky, a visualization tool for multi-messenger astronomy.
Hi, can you hear me?
Yes, we can.
Okay, I'm going to share my screen. Are you able to see it correctly?
All good.
Okay, great. Then I'll start. So, hello everyone. I'm Nuria Alvarez Crespo. I'm the ESA Sky Support Archive Scientist. And today I'm going to present ESA Sky as a visualization tool for multi-messenger astronomy. And this presentation is on behalf of the entire ESA Sky team. So first, I'm going to present a little bit what is ESA Sky, how to access this tool. Then I'm going to present what's new in the new release of ESA Sky that we recently launched and what's the future plan for this tool. So ESA Sky is a multi-wavelength and a multi-mission portal, and we data from a dozen of space missions from the archive of ESA, NASA, and JAXA in all wavelengths, from the radio waves to the gamma rays. So it gives astronomers an easy way to access high-quality scientific data from a computer, tablet, or mobile phone in an interactive and user-friendly platform. So it is designed by scientists with the needs from the scientific community, and it's continuously evolving with the addition of new data and new features requested by the feedback given by scientists. So here I'm going to present to you a little bit the tool. So you have to go to sky.esa.int It's available in 3 languages, English, Spanish, and Chinese. And there are 2 modes. Scientific mode is for professional astronomers, and Explorer mode is more for outreach. So you can pan around the sky, play around, see what's out there, or you can choose to go to your favorite object. Now I'm going to M82, and here you have the view of this object in the optical. You can select any wavelength. So now I'm going to select it in the soft X-rays. This is the view of this object in the soft X-rays, so you can easily change from one wavelength to the other. You can also see that we have a lot of observations from different missions, so you can see what is available in the region of the sky you are observing. This is all the observations available from HST for that region of the sky. We have a good amount of catalogs overlaying right now with the Gaia catalog. So this is everything that is available on Gaia. You can access spectra, light curve. You can access external data centers. You get the idea. So, and also you have access to different publications. So this is all the objects in the sky that have publications associated. So you can choose any object, go to ADS, and also we have an observation planning tool for the James Webb Telescope. And on a personal note, I like to use this sky not only for my research, but when I have it open, it gives me an idea of the panchromatic view of a source, a quick, easy way to see how a source emits wavelengths, and also reminds me that I'm an astronomer. So what I'm doing with all the spectra and light curves and Jupyter notebooks, it makes sense that it's on the sky. So there are more ways to access EasySky in addition to the EasySky interface on your browser. One of them is PyEasySky. So PyEasySky is developed to work on a Jupyter notebook. So this is very convenient for creating a reproducible session for when you want to publish a paper or to share some results with collaborators. Also, we have the AstroQuery module and Table Access Protocol. So this module supports cone searches and download of data products from all missions available on EasySky. And now it also gives you easy Python access to both targeted and serendipitous observations of any solar system object. Additionally, we have a JavaScript API, so you can embed EasySky into a web page or a web application. So since it is designed to be useful for the scientific community, feedback is super important to us. So we get feedback from users through Help Desk or the User Eco Forum. So please consider contributing to this with suggestions to help us improve. So the last version of EasySky was launched last week on October 20th with new exciting features. So one of the new features, probably the most visual one, was a collaboration between the EasySky and the Hubble teams, where we included on EasySky more than 2,000 outreach images curated by the ESA Hubble team into EasySky. So if you again go into EasySky, I'm going to show you what it is. So they are available on Explorer mode because these images are curated for outreach purposes. So you have to go to Explorer mode, and you can change between scientific mode and Explorer mode easily, not only at the beginning. And if you go to the Hubble icon, you can see all the outreach images that are available for that region of the sky. So this is the Hubble images that is superimposed to that sky region. Play around with the opacity. You get also the text that was made available by the Hubble team. Play around in the sky, see how many images are available. Or again, you can go to your favorite object. Mine is the Crab Nebula. So now I'm going to the Crab Nebula, and here you can see as green rectangles how many images are available or in the list. You can click on the list and see the gorgeous images of the Crab Nebula superimposed to the sky. So you can see more images, play around. And I like a lot from this tool that you can see the size of the sources. So for instance, here you can see the size of the nucleus of the Crab Nebula compared to the extent of the entire object. I think this looks amazing. I could play this with this tool all day. So the next addition in this Sky data release is Cheops was added, the light course. So Cheops is an ESA mission that was launched on December 2019 and is dedicated to the study of exoplanets orbiting bright stars to make high precision observations of this planet using the transient method. A transit is when a planet passes directly between the star and the observer. So the light of the star is dimmed, and this is visible in the light curve. So now the light curves of this mission are available on ESA Sky. So again, choose your favorite object, go to spectra and light curves. And here you have the optimal light curves from the Cheops data. You can download it, or you can see the data reduction report and all the information that is available in this report. Now, I would like to focus on our plans to make ESA Sky a useful tool for multi-messenger astronomy. So historically, scientists have relied almost exclusively on electromagnetic radiation to study astronomical sources. So this is visible light, X-rays, radio waves, etc. So this changed in 2013 with the discovery of neutrinos out from our solar system, and in 2015 with the discovery of the first signal of gravitational waves. So these discoveries consolidated the importance of multi-messenger astronomy, where rather than light, we use messenger particles to study astronomical sources. This is neutrinos, gravitational waves, or cosmic rays, that they provide us different information from the sources, or complementary information, let's say. So the advent of new multi-messenger observatories in the next years will drastically increase the number of detected sources. For instance, in gravitational waves, it is expected to detect several per month or even per week. So they will need prompt follow-up to determine their electromagnetic counterparts. So optimize the usage of archives is really important. So it is necessary to have common platforms to store and analyze multi-messenger data. And also archival data can be used to identify already known sources among the various electromagnetic counterpart candidates. So we intend to make ESA Sky a common platform and a useful platform to store and analyze multi-messenger data, making possible to combine multi-messenger data with electromagnetic data for their study. So as a first step, we included gravitational waves into ESA Sky. Gravitational waves are ripples in space-time caused by some of the most violent and energetic processes in the universe, such as collision of compact objects. So as a first step, we added the 56 events from the O3 observing run from LIGO and Virgo in ESA Sky, and it's possible to see the 50% and 90% contours and the probability maps. So we created a multi-messenger icon that you can see like two compact objects colliding. So you have all the events, you can access the event page, and if you extend the table, you have a lot of the information for the events. We didn't include the rejected ones. So you can access the web page. Yes, okay, sorry. And if you click on an event, you can see it in the sky, you can see the probability map, you can see the 50% and the 90% contours, and you can play around with it. So you can see the optical sky with the contours superimposed. You can see the image observations that are available for that contours, the catalogs, the spectra. You get the idea. So again, this is the first step. So as a future plan, we are speaking with the IceCube collaboration, and we are planning to include their data inside ESA Sky. And additionally, in the future, we also want to provide a service of real-time alerts to make ESA Sky useful for the multi-messenger community. Apart from multi-messenger astronomy, we are planning to include the eROSITA data in future releases. So stay tuned. And this is it. Thanks for listening. Again, please, feedback is really important for us. So consider giving us feedback. And here I give you with several resources for this time. Thank you.
Thank you very much indeed. We have some time for questions, and we do have some on the Discord channel already. Agnes would like to know whether you could elaborate on the JavaScript API and whether you could tell us whether you can add custom functionality to your embedded ESA Sky platforms.
Sorry, can you repeat?
Can you elaborate a little bit on the JavaScript API?
Yes. That I'm the astronomer, so I don't have so much details on the JavaScript API. I think it's better if the engineers ask this question. So answer this question, sorry. So please write it on the Discord channel, and the engineers will be able to answer this question much better than me.
Thank you. Nick wanted to know whether there are solar system objects in the platform, and that was answered already. That is the case. And then Thomas would like to know whether you can access the HST outreach images with other clients through VO data access standards.
It is in our future plan. So now it is impossible, but it will be possible. So if you want to contact us again with feedback, we will be glad to listen to your suggestions.
Thank you. And finally, Matthias has pointed out that there actually is a poster on the API, and you can find the link on the Discord channel.
Yes, please.
If there are no further questions, let's thank the speaker again. Our next presentation is by Austin Shin, who will talk about a globally distributed and scalable data path processing framework for Wallaby Science.
Hey everyone, my name's Austin and thanks for coming to my talk. I'm going to be sharing the work that I've done on a new data post-processing framework for the Wallaby Science team, which is done as part of the Australian SKA Regional Centre Design Study. So first, what's the motivation for this work? Well, the AusSRC has access to the two SKA precursor telescopes, and we work with the science teams to develop an understanding for how these SRCs might be able to operate. The diagram on the right shows how we're involved in this process. So data comes from the instruments and undergoes science data processing, which is still on the telescope side.
It seems we are experiencing a small technical glitch.
I'm going to be sharing the work that I've done on a new data post-processing framework for the Wallaby Science team, which is done as part of the Australian SKA Regional Centre Design Study. So first, what's the motivation for this work? Well, the AusSRC has access to the two SKA precursor telescopes, and we work with the science teams to develop an understanding for how these SRCs might be able to operate. The diagram on the right shows how we're involved in this process. So data comes from the instruments and undergoes science data processing, which is still on the telescope side, and then it comes to the SKA regional centres before being disseminated to users. And for this design study, the users are the scientists involved with the surveys on the left. So we have POSSUM, EMU, Flash, EOR, and Wallaby. And I've been working with Wallaby over the last few months, so the rest of the talk is focused on their post-processing requirements. To give you an overview of Wallaby, it's a ASCAP neutral hydrogen all-sky survey, and it's very exciting because it provides a map of neutral hydrogen that's significantly better than what was available previously with HiPASS. So it has much better spatial and spectral resolution and greater sensitivity, And yeah, we're expecting to detect 500,000 galaxies and process data on the order of 6 petabytes by the time the full survey is complete. So yeah, it's a new big data problem, and currently we're in the pilot phase, and we are working with Wallaby in this pilot phase to develop a post-processing framework. So this flowchart summarizes the activities involved in Wallaby's data post-processing at the moment, and this takes data from the telescope and generates the advanced data products, which are tables that scientists can interact with of the sources in that patch of sky. So the first step is data retrieval, where data is copied from CASDA, which is the telescope archive, into our computing resource. Then we do mosaicing, where 2 footprints, which are slightly offset images, are mosaiced together to generate a higher signal-to-noise image that is ready for source finding. The source finding has 2 steps. First is the execution of an automated source finding application, which will generate a bunch of detections with properties. And then there's a manual step involved where a project scientist will look through those sources and verify which ones are real and keep the real ones for the final catalog. And then at this point, the data is either shared to the users, or we have collaborating institutions that will use this source data to generate advanced data products, so kinematic properties by the Canadian Institute, CIRADA, and multi-wavelength properties by the Spanish SK Regional Center. And as the AusSRC, we focus on the stuff above the arrow, so data retrieval, mosaicing, source finding, and then user access. I'll go through different parts of this framework, and I'll start with the computing pipelines. So we use a tool called Nextflow to compose pipelines which capture the steps that I mentioned previously. And you can see that in this diagram here. The pipeline at the bottom there has 3 steps that you saw before. And yeah, they run on a high performance computing resource, Slurm cluster. And yeah, one of the good things about Nextflow is that you can take a pipeline that's composed and run it on any cluster of that nature. So you can run it on any Slurm cluster or other HPC clouds that are available in like Google or AWS or whatever. And the way that these pipelines are composed is really nice. So you can see a little code snippet which shows you how the main pipeline is structured. We have a download, mosaicing, and source finding component, and the main pipeline just takes in some SBIDs, which are identifiers for the footprints that you want to process, and then you just execute these 3 different components, and the output will be the data that you want to generate. So that's a quick overview of the highest level of this pipeline. But I'll go into the components in a little bit more detail. So I'll focus on the source finding component, which is quite interesting. You can see in the code snippet on the left how this source finding workflow component is structured. So there's a collection of configuration steps, followed by the execution of the source finding application, Sophia, and then Sophia X, which is used to take the output of Sophia and put it into a database. And yeah, on the right, you can see how each of the processes are defined. So we have some container, which determines the execution environment. And yeah, each of these processes runs inside a container. And the script that you want to execute is really straightforward. You just run the pre-installed application, Sophia, with the parameter file. You can see at the top there. And yeah, it's as if you were running this on your local machine. So yeah, it's a really nice way of composing different processes that have different dependencies, and you don't need to worry about any of the dependencies because you're using containers. So want to go further into one of the processes. So I want to talk about the source finding application. What I want to illustrate here is that the application for doing the source finding is something that has been contributed to us by the scientists, and we just use their code as part of this pipeline that does a bunch of the different computing steps required for their workflow. So Sophia 2 has been developed by members of the Wallaby team, and all we've had to do in order to run it is containerize it and then put it in our Nextflow pipeline. So it's a really nice way of taking code from scientists and letting them use whatever tools they wish and running them on our system in this nice way. So that was the computing part. Now we've got the database and access to that, which is quite important in this workflow. So we have a Postgres database that stores all of the detection information and the source information, and then both the community and the project team will have access to that. So as I mentioned previously, the project team will have to manually inspect the output of the source finder to verify that the source is real, and you can see the schema on the left. So you have the detection table with all of the properties and products from the source finding application, and then you have a source table with just a name, and that name is the name determined for that source by a scientist once they've decided that it is a real source. And the project team will write to that source table through a JupyterLab interface, which runs on top of Open On Demand. So that Open On Demand provides the view into the cluster, a graphical view, and we use Django for the object relational mapper that allows these users to interact with this database in Python and using Python objects. And the same interface is provided to the community as well, except they have read-only access rather than read-write. And this means they can use these notebooks to either download the data to run on their local machines, or as the notebooks can be used as a place to do their own custom analysis. They can also use IVOA to use tools that they're familiar with, like Topcat. So there's a bunch of interfaces that we provide to access the data. And I also wanted to mention that the generation of advanced data products is a collaborative effort between the AusSRC and Cerrado and the Spanish SKA Regional Center, which I mentioned previously. So we're also developing this network of replicated databases where different tables are shared between us, depending on the data that we're generating. And Manu from the Spanish SKA Regional Center has a poster on how we're making use of Picado to do this. So go check that out if you have the time. And that covers each of the different parts of our processing framework. So hopefully you can see that we have this computing part, which is what does the bulk of the data post-processing, and then a platform part which facilitates this processing and allows us to execute these pipelines and provide interfaces for the scientists to interact with their data or to share the data across other regional centers. So the diagram on the right covers the technologies that we use. We are lucky enough to have access to an OpenStack cloud allocation from the Pawsey Supercomputing Center. This gives us lots of flexibility to play with the tools that we want. We've installed a Slurm on that and BGFS for a POSIX file system. And on that Slurm cluster, we use Nextflow for these pipelines and Singularity and Docker for containerizing the applications that we run in those pipelines. And we also have Jupyter Hub that allows for the manual interaction of data. We have a few interfaces. So Open On Demand gives the users a graphical view into the system. And we also have IVOA for access via popular tools in astronomy, and then Django for interacting with the database, which is a Postgres database, and we have Picado for replication. So the technology stacks that are required for different types of users are completely separate, so scientists can use whatever tools they want for writing their code. Developers of pipelines in this system just need to understand how to use Nextflow and to containerize applications, and then your system administrators have to understand how to maintain the Django ORM or interact with SQL to maintain the database. And yeah, this framework is being used for the pilot phase 2, and we're using this phase to test out the system and make sure there are no more bugs before it moves into a production setting. And yeah, from there we intend to automate the operating of this pipeline, so the execution could be automatic instead of manual. We want to provide an interface to look at the progress of the survey, so see what data is available in the archive, see what's processed, and look at that visually. And all of this is being contributed to a more generic cloud platform for processing of astronomy data, which we call the Radio Astronomy Data Enhancement Cloud, and that's something we're working towards, and the pipeline that we've developed will contribute to. So yeah, thanks for listening to the talk. If there are any other questions, feel free to message or send me an email.
Thank you very much indeed. I see no questions on Discord. Are there any questions in this room? I see none, so if there are any follow-up questions, please do use Discord to ask them or send an email. Let's thank the speaker again. Our fifth presentation in this session is from Julia Healy, who will talk about managing the data flow of a Mongoose survey with open access tools.
Hi. Good morning, everyone. My name is Julia Healy, and I'm going to talk to you a little bit about how we within the Mongoose survey are using some open access tools to manage our data flow. I'm going to talk to you from the perspective of the Mongoose survey team, but much of what I'll show you today is also in use by the Meerkat Fornax team. And in fact, they laid the groundwork writing many of the scripts that form the foundation of what I'll show you. So this talk is presented on behalf of some members of the Fornax team, Filippo and Paolo and Daniel, as well as the Mongoose team, Owen, Filippo, and myself. So first things first, for those of you that don't know, the Mongoose and Meerkat surveys are two of the large survey projects with Meerkat. Both of these are H1 surveys. Fornax is comprised of a number of different pointings covering roughly 12 square degrees across the Fornax galaxy cluster, while Mongoose is a deep survey of 30 individual nearby galaxies. But both surveys have a large number of observation tracks that have to be individually calibrated and imaged. To date, Fornax has about 48 observations, Mongoose has about 116, and both teams have multiple people working on the calibration and imaging. So we needed a way to be able to keep track of which observation tracks have been observed, what has been processed, who's doing what processing. And we also needed a way to keep a record of what was done to the data so that we could keep track of any problems that may arise in the process of the data reduction. So this is just a quick overview of what we need to keep track of. So the Meerkat observations are done in a queue-based system. So we have to submit, the teams have to submit an OPT to Sureo, which contains all of the observing information. Once the observation or track has been observed, we can move the data from the Soraya archive to the computer cluster where we're doing the calibration and imaging. Once the data has been calibrated, we can then inspect the final data product, so the H1 data cubes, for the quality. If there are issues arising in those cubes, then we have to go back and redo parts or all of the calibration. But if it's good, then we can combine that track with other tracks for that target to create the survey data product. So we really only have control over this process once the data has been observed and is on the archive. But it is important for us to be able to keep an eye on what tracks are waiting to be observed so that we can keep an idea of when our data is going to flow. So how do we keep track of this in a way that's accessible to all our team members that are involved in the data reduction? Well, our solution has been to use GitHub, and we chose it because it's largely because it's free, but it's also very visual and has some very useful built-in project management tools. So we can create issues for each track, and this enables us to keep a record of what's been done to that particular observation. GitHub's labeling system also means that we can, it makes it very easy to search through the issue lists for different issues that might appear. GitHub's code repository also means that we can keep track of all our configuration scripts and tables containing the observation information. And we can also keep track on what changes are being made to these files. But also more importantly, another really useful thing about GitHub is that the command line tools mean that we can build in an automated connection between the data reduction pipeline and the information being added to each issue. And we do this using an SSH connection to GitHub using the command line interface. And the URL to the command line interface documentation is on the slide. So how do we manage our observations in Mongoose? Well, this is an overview of our project board. This is just a screenshot, and this is how we keep track of all our observations. The tracks are added to the board when the OPTs are submitted. And then at each different step in the workflow that I showed earlier, new labels are added to the track issue. And this moves each track along the different columns of this project board. Once the tracks are processing on our cluster, they're assigned to a particular team member who's then responsible for the quality assessment. Once they've deemed the data ready, it gets moved to the final column and it's then moved off onto another board. We also have, we keep a record of which galaxies we need to go back and relook at. So at the heart of our tracking are these GitHub issues. So these are created for each observation track. So this means for Mongoose, for our 30 galaxies, each galaxy will have 10 issues. We've developed a series of Python scripts which wrap around the GitHub command line interface so that we can add new issues when the OPTs are submitted fairly easily and automatically. And then once the observations are done, a similar set of scripts will add the observation ID to the existing issue and update the labels so that the card moves along the project board. The automation of the cards is done using GitHub Actions. And if you want to know more, you can check out the URL there. And this screenshot just shows you an idea of what one of the initial beginning parts of the issues for a particular track looks like. So this particular galaxy had been observed. We'd added the labels and that had moved it along our project board. So how do we keep a record of the data reduction process? Well, our data reduction and calibration is done using the Caracal pipeline. We do all the imaging with that. I'm not going to go into the details of how Caracal works, as that's another entire talk. But I will encourage you to go and have a look at Chitit's poster on Caracal, and I think it can be found in poster room 5. So Caracal has some really useful features that help us keep clear records of our data reduction. The detailed log files contain all the observation information, such as how many dishes were in use, the various flagging statistics. The pipeline also produces a number of diagnostic plots that we use to assess the quality of the calibration process. And all this information is collated into a series of calibration reports using some custom Python scripts. So these calibration reports are written in GitHub Markdown. They're separated into 5 different sections, which are automatically uploaded as separate comments to the issue for that particular track. For those that are interested, the 5 sections are the observation info, which is shown on the screenshot on the right. The information on the cross calibration, flagging of the target, the continuum images after self calibration, and then finally the H1 line report. So these reports are uploaded directly to GitHub once the pipeline is finished running, which also updates the labels on this particular track. And at this point, we've chosen to use manual intervention to upload the images associated with each report. This can be done automatically, but because we need to manually look at the H1 cubes and manually check the data, this is a good point to force someone to take a look at the reports. So along with uploading the images, whoever's been assigned this report or this track is in charge of checking the calibration. If there are any issues that they note with the data, it can be documented in the top comment of the issue so that we can clearly see what those issues might be. If all is good with the data, then it just gets a calibration good label. If the H1 is good, then it gets an H1 good label. If it needs more attention, then we have a series of labels for that. So that's sort of how we keep track of what's going on. So coming back to this overview of our project, once the tracks have been marked as good calibration, they end up somewhere in the last 2 columns. If there's a bit more attention needed for the H1, they're in the second last column. If all is good, then they go into the final column. Once they've been marked as H1 good, we use another project board to keep track of an overview of the galaxies as a whole, as these will then be combined to form our deep H1 data products. So I'm going to sort of leave you with some final thoughts on how we stayed organized with GitHub. And I will say that this whole environment has enabled us to stay organized and has allowed our team to maintain a central database of scripts and data with other useful information. So the 3 main GitHub project management tools that we use are the code repository, which stores all our files needed to run the pipeline, as well as any other scripts used to create the science data products that are later released to the larger survey team. Also, all the scripts that are used to do all the automation are stored in this repository. The second part is the project boards. And these, along with the issues, allow us to keep an overview of which tracks have been observed or still need to be observed, where they are in the calibration and imaging process. But they also, more importantly, in terms of reproducibility, enable us to keep detailed records of what's being done to the data during each calibration step. And the way that we've managed to automate many of the interactions with these issues as the tracks move through the different workflow stages has meant that we actually stay current on the administration. And the automation has also enabled us to make batch updates to the issues. And this is important as we have so many tracks that will need to be, and issues that need to be created and updated. We've also made extensive use to use the wiki pages quite extensively. And here we keep all the information about the pipeline strategies that we've used, as well as the information about the different software installed on our cluster and some other how-tos associated with the project. So I hope some of what I've shared might be useful for those looking for a way to keep track of their projects. Not well, thank you for listening and happy to take any questions.
Thank you for that very interesting presentation. We do have 2 questions on Discord. And the first one is from Venustiano, who asked whether how you would recommend the use of a tool for non-experts.
Well, I mean, I must admit, when we started using GitHub, I was not an expert. It's very easy to use, and there's a lot of documentation. So it's quite simple to start using, actually, for anyone who's not an expert.
Thank you. And Angus would like to know whether you have any thoughts on how GitHub's boards compare to Trello's boards for tracking things through workflow.
I haven't done any comparisons. We did, when we started down this route, we did look at a bunch of different options. But my research sort of showed that they were all fairly similar at to first order. But we ended up going with the GitHub project boards because it also enabled us to keep everything centralized. And I think the biggest pro with using GitHub was our ability to automate it. And that has been probably one of the biggest wins of doing this, is being able to automate a lot of the updates to our issue tracks.
Thank you. And very quickly, because we are running out of time, a final question. How about Caracal? Is that easy to use for non-experts?
That's probably a question better asked to the Caracal developers. I've been using it for a while. It's pretty straightforward, and their documentation is pretty comprehensive. But I also work alongside many of the Caracal developers, so I always have an inside track there.
Thank you very much. Let's thank the speaker again. Our last, but certainly not least, presentation in this session is by Maria Arevalo Sanchez, and she will talk about the grand opening of a European JWST archive at the
Hello to everybody. My name is Maria Arevalo Sanchez. I am a DevOps engineer at the GISAC Science Data Center in Madrid, Spain. And on behalf of our team, I would like to introduce you today to the European James Webb Space Telescope Science Archive, which is almost ready to enable great discoveries once Webb Telescope is full operating in space very soon. I will give you today a brief overview of the basics of the archive, and after that I will demo you some of the functionalities that we have made available at the European JWST archive. So why there is an European JWST archive? As you might know, the JWST project is a collaboration between NASA, the European Space Agency, and the Canadian Space Agency. And the main reason for having an European JWST archive is to provide the official European Space Agency repository of all the public data that will be produced by the mission. It is also being designed to be a service to the scientific communities, especially the European one, and this project is trying then to provide useful access to the science data products that will be available once WEB is doing science operations. Being designed and developed at the SAC Science Data Center, we have put EJWST data in combination with ESA-SKY. ESA-SKY is the portal that provides an overview and interface with the Astronomy Science Archives hosted by the ISAC Science Data Center. The EJWST archive will become part of the set of the observations available to users. This allows the linkage between JWST data and data from other ESA missions, and is an alternative access point to JWST data. In EJWST archive, it is possible to overlay footprints from planned and existing JWST observations on top of images from different observatory missions, including, for instance, Hubble and Spitzer. We have also added custom JWST view capabilities on this exploration feature that the JWST archive is offering. You can have a look at the poster prepared by Matthias Wonblatt, where you can find extra details on these capabilities. For those observations including among their products, images, or cubes, we have also developed our own dedicated data viewers and will be shown in the demo. Regarding the data ingestion, we have tested with data transfers and the simulated data from STSEIs in April 2019. We also are running the auto-production of hierarchical progressive surveys, the HIPS, and the Hill-Peaks multi-order coverage maps, the MOCs, both being the IVOA recommendations. And although EJWST holdings consist of public data, we are also offering the opportunity to access the proprietary data from STSEI, which is available in the user interface session and in the AstroQuery sessions using STSEI authentications. So proprietary data can also be downloaded and explored in EJWST if the users have the required access credentials. We are also providing access on a TAP Plus REST service. TAP Plus is an extension of the Table Access Protocol, the TAP, specified by the International Virtual Observatory Alliance, IVOA, and the Plus means that the implementation has been extended by ESDC to provide extra functionalities, such as security and user private area, among others. The EJWST archive also has AstroQuery access capabilities. We have implemented an AstroQuery Python module that provides an API, allowing direct programmatic access to the archive. We have also extended it to provide access to resources for running pipeline software and analysis, and we are also working with the European scientific community and consortium teams regarding early mission data access and analysis. EJWST is also providing a web space telescope area in Data Labs, which is the new science exploitation platform which is developed by the Data Science and Archives Division at ISAC. The web area is based in Docker images that are ready to be used to explore and analyze web data by using Jupyter Notebooks, AstroQuery modules, and PyESA-SKY. You can have a look at the poster prepared by Marcos López Caniego that will explain you a bit more about this. So let's now jump directly to the demo to see all this in action. So here it is, the homepage to the European JWST Science Archive. From here, we can start exploring JWST data by searching by target name or coordinates, or we can also filter by proposal ID. We have also direct access to the main functionalities of the application. Let's have a look at the search. Here we have a search form for retrieving observations where we can apply some filters based on coordinate and target name position. We have also some observation constraints where we can provide some observation ID and list of observations. We can also search by instrument and instrument mode. We have also filters in the proposal metadata like PI name or proposal ID, and we can also search by observation date. Let's have a look at one of the proposals ID that we know that we have observations, and let's have a look at the right side of the search form, and we have here the current search that we are doing with the filters that we are applying. We can have a look also at the ADQL query that is being done to the backend service, the tab server that is available for EJWST. And we can see the results that we would retrieve with the current set of parameters that are applied to the search. So let's go to search those observations. While you see here loading all the results in tabular results, if we click in one of the observations, we will retrieve all the details for that observations. On the left side of the observation details panel, you will see all the summary of the metadata of that observation, an image preview if it's available to show, and then on the right side, we will see an sky view around the target coordinates in ESA Sky, and projecting on this ESA Sky instance the footprint of the instrument detector that has been used for the selected observation. We can also add several footprints to this results view. So we can add, by clicking on the observation ID checkbox next to the name, all the footprints that we want to add to the view. If they are in the same part of the sky, you will be able to see them all together. Let's have a look at full screen mode of the ESA Sky instance, and here you can see that we have access to all the functionality that ESA Sky provides. The background image can be customized, so you can select another sky and change between electromagnetic fields. We can also overlay some image observations that are available in that region of the sky. Here we have some optical HST observation. If we click, we will see what's available to show us in this place. So we can select and retrieve some metadata from these observations. We can maybe overlay some Spitzer ones, and you can see here all the footprints from these Spitzer observations. We can overlay as well catalogs. You can see here, for instance, we have a Hubble source catalog sources to be added. We also have the Gaia EDR3 data to be added to the view. And we also are being able, by clicking on this telescope, to project the JWST focal plane for each of the instruments using this feature. So we can add the focal plane for each of the instruments, and we can move it around on top of the observations that we have plotted in the sky. And this is an useful tool for planning observations of JWST. Let's close these panels. Let's go back to the results, and let's have a look a bit further on some other functionalities that we are applying on the results. So let's have a look at how we could retrieve some data products from the JWST observations. Since we are not logged in, we are not able to retrieve any data or any preview. So you don't have access to any preview, and if you want to retrieve data by using the download products functionality, let's select this level that we are showing here, which is level 3. We see that we don't have access to any of the products, only to one, but the rest is private. So let's do a sign-in action by using the CAS authentication service. And on my account, I have provided a valid token, which is granting me access to private data inside JWST MAST archive. So if I will look for the same proposal ID, let's have a look at the results that we were having a look earlier. So we will see that now we have access to the previews, and we can also have access, and we are able now to retrieve the observations, the product observations to this observation. So we have here, you see they have changed color, and now all the products are available to be downloaded. So this will be requested to MAST. We are providing the token. MAST is saying that we are authenticated and authorized to get the data, and MAST is sending it back to us. So here we can have a look at the image data viewer that we have developed for FITS images, where we can zoom in, zoom out, pan around, etc. And I wanted to show you as well how the cube visualizer looks like. So let's go back to the search, and let me look for an observation ID that I know that one of the products containing it is a cube. So here we'll see a new icon that appears that is telling me that this observation has among its products one cube. So if we click on it, we will see this window, which is composed of two panels. The left panel allows users to explore the images in the cube for each wavelength slice. And this right panel is showing the spectrum across the whole wavelength range of the cube at the location of the pixel that you select. So you select, you will be locking the pixel, and then you can play around in the spectrum visualizer. We are retrieving slides from MAST in real time, and they are available to be explored as soon as they are being retrieved. So this is the classic way of exploring ESA Sky data by searching and filtering by target name, proposal ID, etc. But we are offering as well a visual exploration of the JWST products, including all the HIPs and mocks that we are producing for JWST. So this tool, which is based on ESA Sky, is taking advantage of the extended ESA Sky API to create a custom view of the JWST products with a larger level of granularity. We can select instruments and exposure levels, and we can explore within the sphere and check on the mocks and having a look at the JWST observations that are inside it. So if you zoom it a bit here, you will see the available MIRI observations that are available in this part of the sky. Here they are. So we are offering as well an ADQL search interface where you could provide some ADQL queries. And if you are familiar to the Gaia archive, this will be familiar to you. And we are also providing a comprehensive guide of on how to use the user interface, and also how to use the Tab Plus programmatic access, and also some guidelines on how to use the AstroQuery Python module. So this is everything I wanted to show you. So thank you very much. I'm waiting for questions. Thank you.
Thank you very much indeed for that fascinating demonstration. I see no questions on this talk yet. Are there any from the floor? I see none either, so thank you very much indeed again. This brings this session to a close, so let's thank all the speakers of this interesting presentation once more. Thanks everyone for attending, and we reconvene at noon South African time, and that is 10 o'clock Universal time. Thank you very much.
Okay, so welcome you all to the session after coffee break. So I am Sunil Chandra, working at SAO as part of Intelligent Observatory Program, and I will be chairing this particular session. And in this session, we have 4 contributory talks. So the very first talk is on astronomical data approximation based on neural network models. It is by Samu Radova-Ekertina, currently a master's student in cosmic research in Lomonosov Moscow State University. So now I request the speaker to share her screen.
Okay, hello. Can you see my?
Yes,
okay.
thank you.
Thank you. So, hello everyone. My name is Ekaterina Samorodova, and I'm a master student of Lomonosov Moscow State University, specializing in space research. And I'm happy to have an opportunity to present to you the research on the topic of the astronomical data approximation based on neural network models. In my speech, I would like to touch upon the following points. First, topicality of the research. Second, the tasks set and solved. Third, comparison of the results. And after that, I will make the conclusions. So I'd like to begin by the motivation to study light curves of astronomical objects. It is a well-known fact that modern astrophysical catalogs contain billions of records, including light curves, radiation flux observations, which can be useful for solving different astrophysical problems, such as astronomical objects classification or peak intensity prediction. Classification tasks can be accurately solved with spectroscopy methods, but this analysis requires resources and time. And that is why machine learning models trained on light curves can be applied. In this respect, it is important to develop light curves research methods. One of the main problems is the presence of gaps and uncertainties in observations, which makes it difficult to use machine learning to study light curves. And this problem can be solved with data approximation. As it has already been mentioned, there are many problems that would benefit from using machine learning methods. For example, peak prediction is highly important for studying the physical nature of processes inside the stars. Currently, various methods of data analysis for solving classification problems are used, frequently trained on the simulated datasets. This work discusses the usage of various neural network models for approximation of light curves from plastic dataset compared to the existing approach based on Gaussian processes. In this case, the approximation curves are used for supernova 1A type identification and radiation peak time estimation for measuring the quality of the considered methods. The dataset used in this work is plastic, containing synthetic simulations of future legacy survey of space and time for transient astronomical objects. For this work, a minor part of the simulations is taken for a faster assessment of models' quality. And now let's look at the tasks set. At this stage of work, it is necessary to determine the problem to be solved and the methods of solutions assessment. At this point, each light curve is considered as a function of 2 parameters, the time of observation and the passband value, one of the 6 possible photometric LSST passbands. Therefore, the task is to train an approximation model to predict flux values and estimate the uncertainty of the approximation at each point. This can be achieved while minimizing mean square error. After fitting the approximation model, a uniform grid of 500 timestamps values is fixed for each filter. Thus, a 2-dimensional array of values is constructed for further usage in classification and peak prediction problems. An example of procedure outcome for a light curve fitted with a Gaussian process regression is shown on this slide. Gaussian processes mentioned on previous slide are most often used to solve the regression problem on astronomical data. The main idea of this approach is to expand the original light curve by adding new observations from a regression model. In order to test possible improvements, several models have been selected in this work for comparison with the Gaussian processes-based solution. The first model proposed in this study is the multi-layer perceptron model from the scikit-learn library, which contains two hidden linear fully connected layers and uses the LBFGS optimizer, which converges faster than others while fitting to the small input dataset. In this task, the training subset contains about 100 records, and this is the reason why this option seems to be an optimal one. The second model studied in this work is the Bayesian neural network, which can be viewed as a generative model for available functions. Optimal architecture of this model consists of two linear layers with the normal prior distribution for neural weights. One of the main features of the Bayesian neural network is its ability to predict both target value and its expected uncertainty. Finally, normalizing flow is explored. It is a generative model following the distribution of a light curve while training. The main feature of this model is that it aims to reconstruct full probability density distribution. The flows are aimed at producing invertible reconstruction. And now we are moving to the model's testing stage. The next step is to define the quality checking conditions. For this aim, each light curve is divided into train and test sections. After that, each model is trained to predict radiation flux values. Then, models predict values on a regular timestamps grid with 500 values for each passband, as is shown on the slide. Two graphs show approximated values compared to the training values in the left and to the test values in the right. Now let's pass on to the comparison of the results. As has already been mentioned, some models are able to predict both approximated values and their uncertainty. Therefore, the next step is to compare prediction uncertainties for different models: Gaussian processes, upper right corner, Bayesian network, lower left corner, and normalizing flow, lower right corner. As could be seen, the Bayesian model predicts the lowest uncertainty values, while Gaussian processes estimation is too wide for large gaps. Normalizing flow seems to predict uncertainty stripes of optimal width. On the next stage, the approximated values are directly compared to the observed ones using a list of metrics. The obtained metrics are shown on the slide. The average time required to obtain a complete set of approximated curves is also reported here. Thus, neural networks provide results similar in quality to Gaussian processes, while approximating a set of curves with the MLP model requires thrice less time. It is obvious that one of the main aims of this research is to make the problem of astronomical objects classification easier to solve. First of all, light curves are expanded with the use of approximation models. Secondly, gained predictions are represented as a two-dimensional array of numbers. These gained arrays will be collected and used further on as an input data for the convolutional classification model. In this slide, you can see a typical transformation for the light curves. A clear structure of all the 6 passbands can be seen in the bottom slides. The classification model is trained on 60% of the approximated light curves and tested after that on the last 30%. The main aim of the classifier, whose architecture is shown on this slide, is to detect supernova 1A type using approximated light curves. The classification quality is also measured with a number of metrics. The next step is comparing classification quality metrics for the input data obtained with different approximation models. As could be seen from the table, light curves expanded with neural networks are divided into 2 classes with a similar level of quality as was obtained by Gaussian processes. While normalizing flows produced superior quality using regression metrics, The classification mitigates this leadership. In addition, to test the approximation quality, the bolometric peak prediction problem with two solutions is used. The first approach is summarizing all 6 approximated lines and defining the time which corresponds to the maximum of lag sum as peak time. This method can be used for datasets without any known true peak times, which is a common case for real observations. Otherwise, a regression model can be trained to solve this problem efficiently. We trained the convolutional model for peak prediction based on the approximated light curves. The architecture of this model is presented on this slide. All expanded light curves are divided into train and test subsets, and after that, both methods are trained on the first part, and their quality is measured on the second part. After that, quality metrics are computed. The resulting quality metrics of peak prediction methods for all approximation models are shown on this slide. Quite expectantly, the CNN-based model is superior in quality compared to the direct method. Besides, the normalizing flow model shows the best quality for direct method and is similar with Gaussian processes regression quality in the case of using the CNN-based model. In conclusion, I would like to say that in this work, various neural network models for light curve approximation have been studied and compared using different metrics and their uncertainty values. Neural network models have shown comparable approximation quality to the basic Gaussian processes solution. The scikit-learn model with NBFGS optimizer demonstrates the best approximation quality and speed. The source code, the testing results, and the usage examples of approximation models can be found in the full repository following the link on the slide. So, that brings me to the end of my presentation. Thank you for your attention. If you have any questions, I would be pleased to answer them.
A lot of thanks to Katrina to present this very beautiful work of her. So now questions, please. As far I cannot see any question on the Discord channel, so we can have questions from the room here unless we get some questions. Okay, so I can't see any from the room as well. So there is one question from my side. Maybe it's very vague, but how well is your technique suited for the data which is having very a huge data ununiformity in the data gaps? How well it can take care of?
I'm sorry, are you asking about fitting models on data with large gaps?
Yes, exactly. Thank you.
Okay, I want to show again one picture. So in the upper right corner, we can see that Gaussian process regression shows two wide stripe for the blue passband in the end. While other models like Bayesian neural network and normalizing flow models show rather not so wide stripes, and so these models are more suitable in this case for data with large gaps, I think.
Okay, thank you. Now we have two questions on our Discord channel. So very first is like, why do the RMSE look so big, above 1?
Sorry, I have many tables and I can't understand whether this question is about this table or other metrics table, but I can say that that we use not RMSE as a key metric, but MAPE metric as it shows more understandable value that can be easily. So I think that we will answer this question on the Discord chat more precisely.
Yeah, that would be great. So another question I want to take, like, did you compare against the 2D or 1D Gaussian process, a GP on the each band individual or fit all together?
So the comparison of different modifications of Gaussian processes regression lies outside this research, but as far as I remember, this comparison would be somehow presented in the future publication.
Okay, perfect. I mean, we can have further discussions on the dedicated Discord channel for this particular talk. Thanks a lot. So now, next contributory talk is by Cupani Guido. He is from Osservatorio Astronomico di Trieste, so INAF Trieste, basically. He is a researcher at the Italian Institute of Astrophysics, specialized in software solutions for medium to high resolution quasar spectrum. He has been part of VLT Espresso spectrograph, and today he will be talking about advanced data analysis for observational cosmology, applications to the study of intergalactic medium. So now I request speaker to share his screen. Thank you.
The final goal of the present work is cosmology and fundamental physics. To this end, many investigations need luminous beacons at high redshift. If you want, for example, to determine the matter power spectrum at high redshift by measuring the fluctuations in the transmission of the intergalactic medium, you need bright beacon. If you want to measure the abundance of primordial elements, such as deuterium, to test the Big Bang nucleosynthesis, you need bright beacons. To put limits on the variation of fundamental constants, such as the phi structure constant or the electron-proton mass ratio, you need bright beacons. And to measure the variation of the expansion rate of the universe with the Sandage test, you need the brightest possible quasars. Bright quasars and superstable spectrographs. Historically, in the Southern Hemisphere, where we Europeans have the best instruments and telescopes, such as Espresso and UVES at the VLT, there has been a dearth of luminous targets with respect to the North, due to the lack of appropriate surveys similar to the SNOAA Digital Sky Survey. But time is ripe for a change, thanks to new databases such as Gaia, WISE, SkyMapper, DES, and in the future, LSST. However, quasars are rare objects, and high redshift quasars are even rarer, so the problem is a classical search for needles in the haystack. And to save precious telescope time, since one night at ELT is expected to cost about 500 €, one needs the most advanced techniques tailored in terms of success rate and/or completeness. Afterwards, other advanced techniques will be required to analyze the high-resolution spectra of your quasars in the most reliable and repeatable way. Last but not the least, automated techniques allow us to apply the same procedure to data and to simulations, which is a must for the modern precision cosmology and fundamental physics.
The QBRICS project aims to identify new, bright, and high-redshift QSOs, or beacons, in the Southern Hemisphere. We used photometric data in publicly available surveys, analyzed by means of machine learning methods, in order to identify QSO candidates to be observed spectroscopically using facilities in the South. Finally, we use the acquired knowledge to address specific aspects of cosmology. The QBRICS project already produced several published papers. A few more are currently under review, and more papers are yet to come. Note that the problem of finding high redshift QSOs in the sky is actually twofold. We need to distinguish QSOs from stars, galaxies, and other sources in the first place, and then we need to estimate a redshift in order to discard low redshift candidates. The envisioned roadmap to tackle the problem is to create a database collecting photometric data and use it to train both classification and regression models, which eventually allowed us to identify QSO candidates. Here, we'll briefly describe the Kubriks database. We collected data from the SkyMapper and the Pan-STAR surveys, and cross-matched against the WISE, Gaia, and TUMAS catalogs. The most relevant selection criteria are shown in this slide. The most important functionality provided by the database is that the final table collecting columns from the aforementioned catalogs is presented to the user as a live view, where each value can be traced back to the original catalog providing it. In other words, the link to the original catalog is always preserved, and we can switch from one catalog to the other as needed. A simplified version of the database is shown in this slide, where you can see the original catalogs on the left, feeding a number of standardized tables where, for instance, all magnitudes are given in the same photometric system, all object classifications use the same enumerated values, and so on. Each entry is identified by the name of the catalog and a specific source identifier. On the other end, we have the list of sources in the database, identified by a Kubriks ID, or QID for short, and the table providing all possible match between the QIDs and the original identifiers on a specific catalog. These informations are joined together to produce a view with all columns from the different catalogs, and a row for each match. If a single Kubriks source is matched in 2 or more catalogs, it will appear at least twice in this view. The final catalog to be used for training is generated starting from this view, but is filtered through a table specifying, for each QID and property, which catalog provides the most reliable value. The final view has now a single row for each QID, and the column report the best possible values for the source. By using the identifiers, we can reverse the whole process and trace back all entries to the original catalogs. Note that if a new and more reliable catalog is added, we simply need to update this table to switch to the new values.
The first Kubriks selection was based on the canonical condition analysis, that is essentially a higher dimensional selection process based on a linear combination of colors. And we applied this technique on photometric catalogs in the optical and infrared wavelength in order to select high redshift QSO candidates. Since then, however, more advanced techniques have been applied to the Kubriks selection, such as the probabilistic random forest and recently the XGBoost. The probabilistic random forest is a generalization or modification of the original random forest, which is designed to properly handle measurement uncertainties. The idea underlying the implementation is to treat features, that is what we give as input to the algorithm, as a probability distribution function. This treatment improves the performances of the model and allows the probabilistic random forest to easily handle missing data. The XGBoost instead is a gradient boosting algorithm, and this means that the algorithm creates a model which is adjusted to accommodate misclassification, while at the same time controlling overfitting. Both of our models are trained to perform the selection in 2 stages. In the first step, we aim to select quasars among other contaminants such as stars and galaxies that we instead wish to exclude. Once we have a sample of quasars, we wish to remove low redshift sources in order to select a sample of high redshift quasar candidates. This second step, in particular, is not trivial. As you can see from the histogram on the slide, our training dataset is heavily skewed toward a low redshift object, and this skewness degrades the performances of our selection algorithm. We found out, however, that oversampling technique were useful to recover some of the lost performances. As a final step, once we have a sample of high redshift quasar candidates, we apply once again the XGBoost to estimate a redshift for each candidate. Finally, spectroscopic follow-up have been carried out in the past few months to confirm the nature of some of our candidates. And since the beginning of our survey, roughly 350 new high redshift quasars have been confirmed. You can see from the plot on the right the current state of the survey, where red dots represent new identification by Kubriks, while black dots represent objects previously known from literature. As you can see from the pie chart below, after our runs, we found that low redshift quasars are the main contaminants for our survey, while we are able to reliably exclude stars and galaxies. In general, we find a good success rate, but there is obviously room for improvements. And we are currently testing synthetic data to avoid overfitting that can be caused by the skewed redshift distribution, and hopefully improve on the completeness side of the survey.
During the years, we have been putting together a number of workflows to analyze quasar spectra. That means to model their emission and absorption components and extract the information they contain. These workflows must not only be scientifically reliable, of course, but also durable. They must be designed and documented in a way that makes it easy to re-execute them, possibly across long periods of time. And we gradually realized that what we needed was not yet another software tool, but rather an environment to encapsulate all the workflows that we already had and construct new ones. Using a cooking metaphor, we needed a kitchen and a set of recipes, not just a pre-cooked meal. And this was the idea behind AstroCook, a Python package to design and run this kind of workflows in a controlled way. Here you can see AstroCook in action. Its most apparent feature is this graphical user interface, which allows for an immediate visual interaction with the data. The different recipes are accessed to the menus, and here, for example, you see an absorption system being first detected and then fitted with void profiles. AstroCook contains all our accumulated knowledge about the best ways to model this spectral component, first guessing the level of continuum, then identifying the lines, using the fitting line models to refine the continuum iteratively until we achieve convergence and we can validate it chi-square wise. But this is not all, actually. AstroCook comes with also a built-in login system that transforms these workflows into readable JSON files in real time. And this is both a documentation and a way to re-execute the workflows at a later time. Within the Kubrics project, we used AstroCook in combination with another analysis software of ours, QSFit, to analyze a peculiar class of objects from the survey. And this is a good example of how these resources are actually used in practice. These objects are not immediately recognized as quasars from optical observations alone, so we decided to observe them in the near infrared to clarify their nature. We quadded the spectra, flux calibrated them, and corrected for reddening, and so on and so forth. And finally, many of them were identified as broad absorption line quasars, at redshift around 2 or less, with a disproportionate fraction of quasars showing strong iron-2 absorption, the so-called fellow bulk quasars. These are strange objects, sometimes claimed to trace a transitional strong accretion phase in the evolution of aliens. We used the QSFit to estimate the mass of the black holes and add in the ratios, and finally, we found no evidence about the evolutionary scenario for these objects. But anyway, the analysis is still ongoing. Notably, what we are about to do is to publish these results with a full runnable documentation of the procedure we adopted to foster further investigation. The bottom line is that in this era of big data, the most urgent scientific questions in cosmology and fundamental physics can be addressed only with a synergistic approach, combining several state-of-the-art software solutions. This means to cover also all the steps from data mining to data interpretation. And this is our effort and our challenge as we look forward to the next generation of extremely large telescopes.
Thanks a lot, Kuponi and team. It was really a very nice journey through high-resolution spectroscopy of quasars. So now we have time of a couple of questions. And I can see one question by Shaira on Discord channel. So it's like, so what do you do with the low Z contaminants that you are not interested in for Kubrics?
Well, thank you. As a start, I would like also to thank the organizers for the possibility to give this talk. Actually, these low Z contaminants, for example, the one that we have shown are very interesting for science. So we're not, of course, throwing them away. Also, we started the analysis of some of them. But since they are not our main interest, they will be, of course, included in the database, but with specific flags to recognize them. So sometimes also the serendipitous discoveries can be useful.
Oh, perfect. So, do we have questions from the room itself? So we can't see any. Okay. So anyway, we can have dedicated discussions to the Discord channel particular to this particular talk. So let's thanks Kubani and team for this wonderful talk. Now let us move forward to our next speaker, Romanilo Martino. Sorry if I am messing with the pronunciation. He is from the European Southern Observatory, is stationed in the headquarters in Garching. His main field is studying Cepheid stars as a high precision tool to determine cosmic distances, for example, expansion of the universe. And today he will be talking here, the universe speaks for itself, from unsupervised physics to semantic source separation. Let's welcome Martino and team. Thank you.
Hello. Thank you for having me. I hope you can see my presentation now.
Yes.
If so, well, if I don't hear anything, I assume that you are seeing my presentation. So let's roll with this. So I'm presenting this on behalf of the people you see listed here, who have done most of the work, in fact, and especially Nima Seragat, the second name you see there. He was supposed to do the presentation himself today, but then meanwhile he has moved on with his career, so I'll do the presentation instead, and I'll try to do justice to the work we've done. So, the work we've done is part of ESCAPE, and Marco Molinaro has already presented ESCAPE in his presentation a while back this morning, so I'll just do a quick thing here. So it's a big European collaboration funded by the European Commission to bring together particle physics and astronomy in sharing data. And the wider context is what in Europe we call the European Open Science Cloud, which aims at providing an infrastructure to do so in the future, infrastructure and content to do so. As it were, ESCAPE has several work packages. You see them listed here. The details don't particularly matter here. You know, they cover all sorts of tools needed to do this, to share data in a fair way. And I'm going to talk about especially this pink corner down here to the right-hand side, so adding value to trusted content to the archive. This is what I will be focusing on. This is what we've been doing at ESO for ESCAPE. So what we've been trying to do is to explore applying deep learning techniques to enable searches in the ESO Science Archive. Okay, so this is the headline of what we've been trying to do. Why is that? So these are two screenshots from the ESO Science Archive, the Science Portal, and you see that when you log there, the one on the left is a landing page, you're not presented with anything specific, you're presented with the whole content of the archive. The celestial sphere is color-coded and also in grayscales, depending on the type of observations we have in every position on the sky. These are just Hilpix bits. So how do you go from there to these sources you're interested in? And you see we have of the order of 4 million assets. So how do we allow people to find what they need? So we're allowing searches based on the physical properties of the data rather than the technical description of how they were observed. This is probably too small to see, but we have facets, and what we expose to users are quantities like signal to noise, or depth of an image, or the resolution, spatial and spectral, so that they can find the data they're looking for their own size. It's not necessarily based only or primarily even on position on the sky, but really on a physical description of the properties of the data. We also expose more traditional searching criteria, but and we're trying to find a balance between the two. What we're trying to do now is to move even further and really into the properties of the data itself. So first thing in order to do that is to characterize the data at a proper level. And this is what we've been trying to do with deep learning. The first two bullets are what I just said earlier, so it's just for the record. Let me just use a second on the last bullet there, let the data speak for itself. What we've tried to do is not to impose any of our preconceptions of what the data look like, but let the machines find that out. And that is both on practical reasons, because there's just too much data for us to know the content, and also because we don't want to do that. We want users to do their own science, not us imposing our preconceptions on what users might be able to do or not. So we try to have the machines explore the archive without any preconception. And we started as a case study from stellar spectra. So the instrument of choice was HARPS because it had a large archive of the order of 300,000 individual spectra, each with of the order of 300,000 wavelength channels. And we've done it in two ways. We've collaborated with HITS in Heidelberg with this. They chose a fully connected autoencoder with two ranges dimensions. And this is very agile architecture, which is great for speed and interactivity. Well, we are at ESO. We've tried another approach with a convolution, fully connected layers with latent dimensions in the middle, and trying to, without degrading the spectral resolution, trying to figure out what the network learns. And this is what I'm going to concentrate on in the next few slides. After the machine has done its job, we need to turn this into something that's useful for humans. Okay? Otherwise, there's no point in it. This is not an exercise in computer science. This is an exercise in making archive services for users. So we need to ask ourselves, what makes two spectra, in this particular case, two assets, two archive assets similar? Can we assign some physical meaning to what the machine found? And how do we present these results? Okay? And we want to make these services for a larger community as possible. Because half of the, broadly speaking, half of the astronomical community out there uses the ESO Science Archive. That's our target, okay? Not the few who know what machine learning is. So, well, this is just a slide that says, we don't want to do the machine learning, we want to do deep learning because we don't want to impose what the features to be extracted. Let's see if the machine learns it by itself. Okay? So let me move on. This is the design. It's pretty straightforward. We start on the left with our signal. That's the spectrum in this particular case, which is turned upside down here. It's the dimensionality. It's reduced to the middle, the latent space, and then reconstructed again. The reconstruction and input are compared until they're done properly. The reconstruction is proper. And that's when, at the end of this process, the machine has learned. And let's see. This is just an illustration, if the thing plays, of how the machine learns. At the beginning, it starts without knowing anything. I'll just speed it up a little bit. And then it starts to figure out, okay, there's something out there. And then it starts refining this something. It figures out that there are, at a certain point, it figures out that there are lines, sharp features in the spectrum, et cetera, et cetera, et cetera. It deepens them until it finds a satisfactory match. Okay? Now, we started out with 128 dimensions in the latent space. And the machine figures out that not all of them are significant. And by the way, we're imposing some disentanglement to make this interpretation easier. Okay, but only 6 dimensions out of the 128 we started from carry some meaningful information, okay? The machine has learned something not trivial. What is it that it has learned? Can we interpret that? If we now plot on the x-axis are just the number of the indices in the latent space from 1 to 128. And we try to see if those 6 dimensions correlate with known stellar parameters. Radial velocity, effective temperature, this is going in vertically, gravity, metallicity, and airness. And you see that in 3 cases out of 6, it does. The network picks up, that's the second from the top, that effective temperature is a meaningful physical characterization of a spectrum. And so is surface gravity. We didn't say anything to the network about any of this. It's not trained to do this, but it did it by itself. On the other hand, it's sort of, we note, but it's sort of disappointing that metallicity, so the chemical composition of the star, is not picked up as a particularly significant dimension. okay? And we've published this in a paper a couple of months ago. Just a quick note, if we had done the same analysis with simple PCA, the spectra would be reproduced, of course, because PCA is a unique, provides a unique description, a full description of the input, but it doesn't pick up any specific dimension. So in this sense, the PCA is not learned. It can reproduce the spectrum, but without learning any of its characteristics. Okay? So this is where we stand basically on this. The basic idea works. The network figures out that there's something important going on there, and it figures out some of the physical characteristics of the spectra. Some of them it doesn't. We're not exactly sure why. There may be several interpretations. So there's something we need to explore. So a couple of words on another thing that the network seems to pick up. So the network picks up intrinsic astrophysical signatures from the telluric absorption created by the Earth. Okay, so this is one spectrum. The blue is the input. And you see that the network has not reconstructed some of the features in this network. This is the orange one. It does not follow the blue input in some cases. And that's good, because that is input that we're not particularly interested in as astronomers, because that's a signature of the Earth atmosphere, not of the stellar source, of the astrophysical source. So we explore this. We bumped into this by chance, to be honest with you, but then we start to explore this. And so we explored why and how a network under certain circumstances picks it out without being asked to do so again. So the network understands the semantics by itself, and it turns out that the crucial thing here is that it learns it for as long as you're not in the topocentric reference of frame, or frame of reference for velocities. That's the frame of reference that's addressed with respect to the observer, which is a very special frame of reference. If you are in any other frame of reference, so the ones that are useful for astronomy, the network picks up this difference. And you see there how it reconstructs certain features on the right-hand side. So the stellar ones, without reconstructing the telluric sequence, okay? And we're trying also to work out the consequences, also the practical consequences. We're doing that because, of course, the telluric signal is a nuisance to the astrophysical interpretation of the data. Last couple of things, ALMA, we've moved to the next data type. ALMA generates, so this is an array, it's a radio telescope, it's an array, millimeter and sub-millimeter, generates 3D data cubes, 2 spatial dimensions and 1 spectral dimension. What we want to do is to analyze the cubes as they are, 3D. But they're not, as a first step, they're not homogeneous enough to expose them to the machinery directly. So we started with 2D images, so collapsing the spectral dimension. And we're running them through the same machinery as the spectrum, and this is a work in progress. Then we started to build also user tools on top of, user tools on top of the results to try to expose this, and these are just prototypes to give you an idea. So the first one is sliders where you change the weights in the deep learning latent space, and these are the 6 significant dimensions you see here on the left-hand side. And with sliders, you see how each dimension affects the output. So this is a way for users to figure out what is it that the network has learned and make up their mind if it's useful for their specific use case or not. So this particular slider changes the shape of the spectrum, as you can see in the 2 middle figures, well, the figures on the right-hand side, at the center here of the slide. This slider changes the shape of the spectrum. This other slider here changes the position of the lines. It does not so much affect the depth or the lines of the shape of the spectrum, but their position. So this is the data dimension that picks up radial velocity, okay? Then this other one changes the shape of the lines. You can see this in the right-hand side, in these two figures. Sliding this slider changes the shape from very narrow to broad. And this, again, are ways to explore the machine learn and make up for yourself as a user side, whether this is useful for what you want to do with the data. Okay. The other service we're exploring is a similarity search. The idea here is that you as a user, you upload the spectrum you're interested in, and the machinery tells you spectra that are similar to the ones you've uploaded. Okay, and this is a way to skim through the 4 million assets that are in the archive and pick the ones that resemble the one that you as a user are interested in whatever characteristics you're interested in. And that's why you also need to have tools, and that's the thing on the right-hand side, to explore what are the characteristics that the network picked up and made a comparison for. And then you can choose which dimensions, and then you need tools previously to understand what dimensions mean, and we also are developing this connection. I guess this is what I wanted to say to you for today. So thank you very much. And with this, I will stop sharing.
Thanks a lot, Martino. It's really tremendous work, and it's a nice tool. And now we have time for 1 or 2 quick questions. One we already have on our Discord channel by Michelle. And she says like it's a very interesting work, and asking, did you find the architecture of the autoencoder had an impact of the correlation with physical parameters?
Okay, here I'm a bit out of my turf because I'm the astronomer in the situation. So, and again, Nima would have had a better answer than what I can provide, but let me try. Yeah, there are characteristics of the network that influence the output, but not dramatically so. I mean, the fact that basically out of the data set, 6 dimensions are picked up, stays whatever it is that we do, and also the ones that are picked up. We tried to play with its characteristics of the network to see if, say, chemical composition would be picked up, but we didn't manage to do that. So there are, at the fine level, yes, but at the bigger picture level, basically this is what these types of networks pick up.
Perfect.
I hope this answers the question.
Yeah, perfect. Hope. Do we have another last question for Martino on this live channel? Okay. If not, then we can have a further discussions on our dedicated Discord for this particular talk. Let's thank speakers. So for the next presentation, we have, it's basically a recorded presentation by Vincent Picowet, if I'm not making it wrong. So he's a PhD student at Marshall University and Columbia University. He's basically building astronomical instruments, basically UV spectroscopy, detector characterization and all. And he's also working on innovative ways to use visualization and image processing. So today his topic of talk is tackling the issues of image processing via plugins. Example of PyDS9 plugin. So hope the recording will be clear and loud.
Good morning, everyone. So my name is Vincent, and I'm a PhD student working at LAM and Columbia University in Galaxy Evolution and Instrumentation. So for instrumentation, as much as for Galaxy Evolution, I had to go through a lot of image processing. Then today I'm going to introduce you a side project which emerged from this time spent processing images. I will try to convince you that plugins are an amazing opportunity to address the issue of image processing, which is a pretty complex task to handle. As I'm not a software engineer or anything, I might say stupid things at some point, so if I do, don't worry, you will have time to correct me at the end. So I feel that what is image processing is not even that clear. It's more like a continuum that goes from basic visualization, like zooming, panning, scaling, that are handled very efficiently by all fit viewers, to enhanced visualization, which begins to become a standard in modern speed viewers with like 3 or 4D visualization, profiles, catalog overlay, and so on. Then with image analysis, which is different from the above, as it does not only bring qualitative, but also quantitative information. And I only know a couple of applications that address this issue. And then image processing, where we actually change the pixel values for background subtraction, stacking, or other things, and down to research-grade pipeline, where all the above processing can be generalized to an infinite number of images. And of course, as you can imagine, the deeper we go in this processing, the less it is included in current astronomical imaging application. So still, I will try to give some hints about why we need to address this issue, what are the challenges that future image processing applications need to tackle, and why I think that plugins will present a good opportunity to address these challenges. And I will then present an attempt to design such a plugin. So, astronomy is a particular discipline where an essential part of the job relies on image analysis. And it's in addition evolving towards James Gray's force paradigm, basically stating that after science discoveries being driven by empirical evidences, scientific theory, and computational science, now the science undergo force paradigm shift, where discoveries will be mainly driven by data-intensive work. And for science relying on image analysis, processing software must be much more available than what it is right now for the scientific community. And the community that codes, but also the one that does not. Currently, even basic processing, like doing a radial or energy profile or cropping an image with WCS, needs to be recoded, which is extremely time-consuming. So I sent a small survey to lead developers to verify that indeed a small number of apps were allowing such processing, with I think the most complete work in this sense being Gaia from the Starlink project. So image processing is a science-driven, and the needs evolve and differ depending on the science, instrument, and energy domain people work on. And I feel this draws a new challenge for current and future imaging software, which is mimicking what has been done in bioimage software by really addressing image processing. And of course, this is a too complex task to handle for only one full-time equivalent, as we can see here for the different applications. So how do we do it so that it is the most beneficial as possible? Image processing applications will need at some point to allow the entire succession of processing, all the way down from visualization to image analysis and research-grade processing. Second, as all PIDS viewers converge toward high interactivity, processing software need to keep the same consensual feature of interactivity with regions, profiles, plots, and so on. And again, as the needs differ on the type of science you do, and evolve with time, future applications need really to catalyze community collaboration and code enhancement so that it is easier to follow the evolution of the needs. It's time, I think, to aggregate the processing tools developed by different teams around the world and aggregate them wisely as it is done in other fields already. Of course, all these challenges cannot be faced by one full-time equivalent. And for instance, the S9 lead developer confessed that spending on 80% of its time supporting users on maintaining existing things, which gives him only 20% of time to innovate and add new features. So how do we do? I feel the best way of tackling the need of image processing is by boosting or encouraging collaborative development. In particular, let me explain why I feel plugins for PIDS viewers applications are an exciting compromise. First, it allows significant and free innovation without breaking the software integrity. In addition, plugins would lean on already proven PIDS viewers that are stable and easy to use. And then they can take advantage of the already here high interactivity. We have the chance to be in a field where collaborative development is the standard, so let's take advantage of it. There are too many PhD students, even me, recoding existing things, and also algorithms that sink into oblivion each time a PhD student leaves or a senior researcher retires. And it's not a coincidence if a major part of the top 10 of fast-growing open source apps are following this implementation approach. It's because it works, And then, of course, you would say that it's already done in several astronomy tools, and that's true. That's a good thing. And I think we should encourage it even more. We should ask ourselves how to do it efficiently and reproduce existing initiatives that work in other fields. In this vein, I have tried to gather some processing I used and create this kind of plugin. A plugin that tries to answer the three challenges that I described before, and also gather a glimpse of all the possibilities that offer FITSViewer's extensibilities, so that it motivates astronomers exploring this development approach. So I decided to use the FITSViewer DS9 for three main reasons. First, because its 30 years of development has made it extremely stable, and that they always follow the rule, keep it simple. Second, they are the most popular in astro image visualization with Aladdin, which has a slightly different purpose. And also because they allow simple Python extensibility. And then it's easy to understand why I chose Python, despite the fact that I'm lazy. First, to take advantage of the great synergy around it, because it is easy to code, read, reuse, and so on. And that the existing packages like Matplotlib or AstroPy and others allow to implement really easily an infinity of processing codes. So the goal of PyDS9 plugin is to take advantage of visualization application to push it a step further by allowing to analyze image while keeping a high level of interactivity. The processing functions can then be generalized automatically to a set of images to turn the quick look tool into a real multiprocessing pipeline. So I'll just show a video about how it works so that you can see. Let's open an image with DS9. We explain the interaction by the way we use metadata, like regions, plots, catalogs, to improve the communication between the user and the data. For instance, by a simple key hit, you can explore the dynamic of a dark region by computing and applying scale thresholds computed on the encircled regions. If you want to explore the dynamic of the full image, just unselect the region and rerun the analysis. To get a better sense of what is in your image, the same region can be used to visualize in 3D the encircled area. By using the visualization toolkit, you get a state-of-the-art 3D rendering with the possibility to add contours, change the scale, and create animated GIFs. These can also be very helpful for 3D cubes or multi-band images. This plugin incorporates essential functions to support instrumentation or analyze the performance of your data. For instance, by encircling a bright and compact object, you can compute a radial and energy profile. Every DS9 plot, profiles, histograms can then be fitted by different functions, with the possibility to add a high number of spectral features. The user can then change the initial guess parameters to be sure that the fit converges. We added a Python interpreter to have the possibility to run direct transformation or analysis on DS9 images. In one line, you can create artificial images, crop the DS9 image, mask high values, or add noise, for instance. The result will automatically be loaded in DS9. To see the command sent by DS9, just select the analysis command log in the analysis menu. As one line is not enough, we added the possibility to link any Python macro so that people can add their own transformations or analysis in a simple language. The possibilities are then infinite. You can implement and run models, link an artifact detection code, run complex transformations or analysis. The key aspect of all the processing functions is that they can be applied to an infinite number of images by adding to the DS9 command the path of a set of images by using regular expression. This will literally turn your macro into a real multiprocessing pipeline. You can also specify the number of processors you want to use. We also linked the most famous astronomical software to the plugin to allow research-grade analysis and processing. For instance, you can easily optimize a high number of Sextractor parameters by using it with DS9. You can then interactively select the sources, verify their magnitudes, filter, and order them. Once again, when you found your best set of parameters, you can turn it into a multiprocessing pipeline and launch the command on a set of images. Extracted sources of all the images will then be saved in a second. This versatile Python plugin is designed from the ground up to perform research-grade interactive processing of images and to allow scientists to develop their own macro and turn them into important pipelines. Okay, so to conclude, let's combine, I think, the plugin approach with popular scientific programming language to explore the full capability of community-driven image processing. And I think that on the developer side, it's not that hard to do, and there are plenty of interesting examples that worked. And generating the enthusiasm on the synergy might take some more time, so that's why I think that we need to address this issue quickly. So if you have any question or remark, I will be happy to hear them or to talk longer after this session. Thanks for listening.
Thanks a lot, Vincent. It's a fantastic talk. Now we have time for a couple of questions if there. Okay. I can't see any on Discord channel. Anyone from the room? Okay. Not that, then I can take liberty of asking you one question. It's about if we want to model a radial profile as you showed, and is there any possibility to include custom models in fitting the radial profile of any instrument, image from an instrument? Okay, we can't hear you. You are muted.
Sorry. Can you ask just at the end of the question? I did not hear because someone else was talking actually.
Okay, so I am interested to know whether we can have a custom model fitting for radial profiles you provide.
Yeah, actually, so you can add any function to feed the radial profile, and also you can also add to the code itself the kind of the PSF that the size of the PSF that of the instrument, for instance. So there are different things that you can add, but you can also add any function to feed the radial profiles.
Okay, perfect. I'm interested to learn more about this, so we can discuss later on our Discord channel. So now we have 2 questions, so I think I would like to take it. So Simon is saying that thanks very much for the interesting talk. Can you point us to the documentation of the tool? Question is like, where does the macro run, on the same DS9 resource or remotely?
So the documentation, you can find it actually on the DS9 website. So on the DS9, when you go in the install page, there is the link to some video and some documentation. And there is also, when you download the plugin, some tutorial to use actually the plugin. And the macro is gonna run on the displayed image. So for now, it's only on the one that you have on your computer. But as the goal of this plugin is that it's really extremely easy to code, as it's only on Python. So basically, everyone that knows how to code in Python can add its own features and functions. It's what I wanted to stress in this video is really the simplicity of doing this kind of plugin.
Okay, perfect. So it will be better if you can just share the link over here. Next question is by Thomas. It's like a very interesting talk. Do you feel that the Jupyter ecosystem somehow helped to tackle the issue you raised?
Yeah, I think, well, there are plenty of ways to tackle the issue I raised. And I think that's a very difficult question to answer. What is the best way? I've seen that. I think one thing we should do at least is to try to see what has been done for bioimaging. And for instance, there is this software which is ImageSC. I think that gathers all the image processing softwares, but there are maybe 40 applications, but it's all about bioimaging on other things, but none about astronomy. So I feel like we could at least join these things and then think about how we should do it. What I thought is that DS9 is very standard, and then doing just Python packages is really simple to plug it with it, but maybe doing it with Jupyter might also be a wise idea. I think also one important thing to do is to create some kind of platform where we could share these packages. It could be like AstroPy, like associated packages or DS9 associated packages or any other thing, but that's the different aspect that I would see.
Yeah, thanks, Vincent. And yeah, Simone, it's really nice. You can discuss further on the channel. So thanks a lot, Vincent. And
thanks for inviting me.
Before we break for lunch, let us thank all the speakers of the day till now. Now we break for lunch.